In this video, we're going to start chapter 6 on functions of several variables. And we're going to talk about section 6.1. So 6.1 is just the introduction to what a function of several variables definition would be and how to evaluate them and find the domain. So finding a function value for a function of several variables, how to use function notation, and finding the domain of a function of several variables. All right, so here's our definition. A function of two variables assigns to each input pair xy exactly one output pair f of xy. So up until this point, we've been dealing with functions of one variable, that's the f of x, that represents y. So this time it's f of xy, so your domain is two-dimensional, represents exactly one output number, f of xy, and we typically call that z, as for the ordered triple to end up being xyz for the solution. All right, so we're just going to start with an example of plugging numbers in. So for the profit function, p of xy equals 4x plus 6y, find p of 25, 10. So here, x is 25, y is 10. You just substitute, just like if you were doing a function of one variable, f of x equals something, you plug that value in for x. This time you plug in two values for x and y. So we plug in 25 for x and plug in 10 for y. Simplify. We end up getting $160. All right, so here's one you can try on your own if you'd like. A company's cost function is given by c of xy, equals 6.5 times x plus 7.25 times y. Find c of 10, 15. So x is 10, y is 15. We're going to substitute that into the equation. So 6.5 times 10 plus 7.25 times 15. Simplify. You should end up getting $173.75. The total cost to a company in thousands of dollars is given by c of xyzw equals 4x squared plus 5y plus z minus natural log of w plus 1. So this time we have a function of four variables. Okay, so where x dollars is spent for Labor Day, or for labor, y dollars for raw materials, z dollars for advertising, and w dollars for machinery. Find c of 32010. So here the x value is going to get plugged in for, or 3 is going to get plugged in for x, 2 for y, 0 for z, and 10 for w. So we get 4 times 3 squared plus 5 times 2 plus 0 minus the natural log of 10 plus 1. Clean that up. They've rounded off the value of natural log of 11. And then simplified, and we get approximately 43.6 thousand, right? Because it said that the cost was given in thousands, which would end up being $43,600. Pay attention to the units right here, okay? You might have to convert your answer. All right, the second objective of this section is to learn how to find domains. We will only deal with functions of two variables when we're finding domain. Okay, although in terms of just defining a function, you can define it of however many variables you want. All right, the domain of a function of two variables is the set of ordered pairs for which the function is defined. So instead of just the set of x values for which the function is defined, like a function of one variable's domain would be, now we're looking for this set of ordered pairs because our domain is two-dimensional. Determine the domain of each of the following. F of xy equals x e to the power xy. E to the power square root of y. The second function we're going to look at, g of xy equals the square root of y minus 3x. And then the third one, h of xy equals 1 over y plus x squared. All right. So for the first function, for this function, x can be any real number, right? It's just x times something. But since y is under a square root, this function, I changed it here. In the original page, it was y. It was just a y. We're going to look at if there's a y plus 2 under there. But since y is under a square root, that expression under the square root, y minus 2, must be greater than or equal to 0. Otherwise, you'd get an imaginary value. So the domain in set builder notation would be the set of all xy such that the y value for solving this inequality is greater than or equal to 2. So x can be any real number, but this is a restriction for y to make sure we don't get a negative under the square root. All right, for b, it was this function. This time, this whole expression y minus 3x is under a square root. So here we want y minus 3x to be greater than or equal to 0. So the domain would be the set of all xy such that y minus 3x is greater than or equal to 0. And you could leave it like that, or I think they're going to give you multiple choice, and you might just be filling in the blank for the set builder. You could write it as y greater than or equal to 3x, right, or just list it as this. Here, h of xy is 1 over y plus x squared. So here we do not have a square root issue, but we do have a fraction. So here the denominator, y plus x squared, would not be allowed to equal 0, because you can't divide by 0. So your domain would be the set of all ordered pairs xy such that y is not equal to negative x squared. Right here, they did just move this x squared to the other side. Okay, so you're listing restrictions on one or both variables to make sure that when you plug numbers in, that you're getting a real number answer. All right, so that is it for this section. Our summary here: a function of two variables assigns to each input pair xy exactly one output pair f of xy. A function of two variables generates points x, y, z, where that z coordinate is your function value, f of xy. The graph of a function of two variables, we didn't talk about this, but if you were, because we're not going to do graphing, but if you were to graph a function of two variables, it's a surface, and it requires three-dimensional coordinate system. So it's not just a curve, right? It would be a surface like a plane or something like that. And then the domain of a function of two variables is the set of points in the xy plane for which the function is defined, and that will just depend on the function. Okay, you have to make sure that you're not square rooting negative numbers and that you're not dividing by 0. And if you had a logarithm, that there's not a negative expression inside of a log, things like that. All right, so that is it. That is the end of that introduction section 6.1.